Hi, this is the MAE 152 jack stand group, and this is our final project video. This is a typical loading case for a jack stand. Here you see the jack stand underneath the vehicle at a jack point, and you have a jack here. These are the original parts. Here we have a jack stand, and this is the pin. The materials for the jack stand, everything is essentially an aluminum alloy besides the pin, which is made out of steel. These are the boundary conditions that we analyzed. For our initial boundary conditions, we fixed one edge in all degrees of freedom and had rollers on the rest of the face. And another condition that we analyzed was having only one node specifically fixed and then having two other nodes with rollers. And then both of these cases were simply supported. The types of loading that we analyzed was a distributed load in the center face of the top of the jack stand, and another load case that we analyzed was applying all the load onto just one lip of the jack stand. Here for our design iteration, we determined that the pin was a limiting factor for our jack stand in terms of capabilities. So what we did was increase the diameter of the pin and also the hole diameter in order to improve the design of the original jack stand.
Hi, now we're going to go through the studies of the original design. So the original design, we put a 2-ton distributed load that's on the top of the jack stand, and it has simply supported boundary condition at the bottom face. So these are the results from that study, and we see that there's a concentration of force where the pin is interacting with the two parts of the jack stand. We see that the maximum stress is around 30,000 psi, which is pretty close to the yield strength of the aluminum alloy. Here we see that the pin is stressed, but still not nearly as stressed as aluminum because the pin is made out of steel. But you see that there's still a high concentration of stress on the area where it interacts with the jack stand. So we wanted to test to make sure that this was correct. So we did a closed form solution where we modeled a hollow cylinder part of the jack stand and put a 2-ton-pound force on the top of the jack stand. It was also simply supported. When we did this, we calculated all the math out, and we figured that the average stress on the cylinder should be around 3,018 psi. We also ran buckling just to make sure that the buckling wouldn't be too significant. But with this closed form solution, we see that we have a pretty good agreement with our model, because on the original design, the area that is highly stressed is only where the hole is, where the pin goes through. But on this area, we see that this is much closer to the 3,000 psi estimated average stress the closed form solution provides. But we see we have like a 5% to 49% error, but that's really just because of the hole, which was not accounted for in this closed form solution. We wanted to verify that our boundary conditions chosen to model the jack stand were accurate. So we ran study A-1A, but with new boundary conditions, boundary condition B, where we have 3 nodes which are the fixed portions of the model. 1 is fixed and 2 are rollers, so it's still simply supported. But we found that this really did not work out well, because the areas where the geometry was held were an order of magnitude 10 times higher than the yield strength of the jack stand. So this is a comparison. We see that there's a huge difference between these two boundary conditions, and because boundary condition A accurately modeled what the advertised 3-ton jack stand advertisement, we decided to go forward with that load or boundary condition. So our next load case was a 1.5-ton load that is distributed on the side lip of the jack stand. It's still a simply supported boundary condition. We went with boundary condition A, and we see that these results are pretty interesting. Where the force is applied, we see that there's concentration and stress on the top surface, but also on the sides where the top part of the stand is bending. It's not as significantly stressed as the 2-ton load applied to the top face, but we still see that this is a case of extreme misuse, and we still see these concentration of stress on the pin. The next study we did was a buckling study to make sure that buckling was not a problem. It's still a 1.5-ton pound force load distributed on the top surface, and it's simply supported. But we see that we have a load factor of 39.766. So buckling is not significant. It's not going to fail by buckling. So our video has been running quite long, so we're just going to very quickly go through the results. These are the static results and the buckling, and the model is listed on the next page. This is design iteration 1. These are the model studies for both design iterations, and we see that the frequencies are quite high, so they are not significant factors of failure for this model. Here is the improved design study results, and here is a comparison between the two. And this shows the buckling comparison for the two design iterations. Thank you very much.